Hey guys, this is Mr. Pinter again. Welcome to Chapter 6 on time and frequency characterization. In part 1 of this video, we'll be looking at Bode plots. Bode plots are an important tool that we're going to use to look at the frequency response of a system, in particular for filters. So this is a short chapter. There's just two parts here. In this part, we're going to look at Bode plots, and in particular, we'll show an example of how to construct Bode plots for a very simple RC low-pass filter. And I'll also show you what I call the shortcut method for Bode plotting, and this will also help you with some of the homework assignments for this chapter. And then in part 2 of this chapter video, we'll look at LRC filter design, and this will be some important information for the filter project, which is something that we'll start thinking about next. So let's get started with part 1 on Bode plotting. So if we think about the frequency response of a system, for example, let's say we have a low-pass filter. We know that the frequency response is a very important function to plot because it tells us how the filter behaves at different frequencies. So what we've been working with so far is this plot over here, and what we're basically plotting here is the magnitude of the frequency response. So we have h of j omega, and we're going to plot that here. And we're going to just plot it versus omega, versus frequency. So this is a linear graph of the magnitude of frequency response versus frequency, versus radian frequency. And again, this is our low-pass filter. You can see that at low frequencies, the filter is basically, the magnitude is close to 1, so it's just going to pass basically any low frequency without affecting it at all. And then as we get to higher frequencies out here, you can see that this filter is going to block any signal coming in at these higher frequencies because its magnitude here is very small. It's a small fraction of 1, and meaning, that's what it's going to multiply the signal by. So it's effectively blocking it. Now, there's another way that we're going to explore in this lecture on how to plot this, and this is the Bode plot, or in particular, let's look at the Bode magnitude plot. So the difference here is instead of a linear plot, it's a log-log graph of magnitude of frequency response versus omega. So what we're plotting here in the vertical axis is we're plotting the magnitude of hj omega in units of decibels, or dB. And the way to calculate decibels is you take the log of the frequency response and then you multiply that result by 20, and that will give you decibels. So this is, it's a logarithmic scale basically, okay? And this is, so we're plotting decibels here, and you can see the frequency here is plotted on the horizontal axis, but this is a log, it's plotted on a log scale. So you can see the frequencies here in radians per second that go by decades, orders of 10. So we have 1 radian per second, 10, 100, 1,000, 10,000, and 1 million. So to construct a Bode plot, and we'll go through an example shortly here. Basically, the first thing you need to do is find the frequency response of the system or the filter. And then you're going to determine the magnitude and phase using the normal methods of finding the magnitude of a complex function and the phase of a complex function here. And then we're going to plot the magnitude of the frequency response in units of decibels. And again, 1 decibel is equal to 20 times the log of the quantity that we're plotting. So, we're going to plot 20 log h of j omega, or I should say magnitude of h of j omega, versus omega, and we're going to use a log scale for frequency. So this is the Bode magnitude plot up here. This is some other system. And then down here is likewise the Bode phase plot. And the phase is, the phase angle over here is shown in degrees or radians, but this is not a log scale. But again, the frequency is always shown on a log scale. There are several advantages of using Bode plots, and those will become more apparent when we start constructing and analyzing Bode plots. But one of them that we can see right off the bat is that by using a logarithmic scale for frequency, we can plot a large range of frequencies without having the graph being so stretched out. So, you know, a typical Bode plot might go to millions or tens of millions or even hundreds of millions of radians per second, or hertz, depending on the units used. But we can do this with just, you know, using just a few orders of magnitude or a few decades of frequency. So our first example to see how to construct and analyze a Bode plot will be for the simplest, probably the simplest system that we can think of, and that's an RC low-pass filter. So this is the RC, the same simple RC low-pass filter that we introduced back in Chapter 3. So I'm not going to go through the details of deriving the frequency response, but just to refresh your memory here, this is the filter itself. It's one resistor, that's the R, and one capacitor, that's the C, and they're configured in this configuration right here. The input voltage signal comes in here on the left, and the output voltage is taken here where the resistor and the capacitor join. And the frequency response for this filter, we did the details in Chapter 3. The magnitude of h of j omega is given by 1 over square root of 1 plus omega RC squared. And also remember that this is the frequency response plotted. This is not a Bode plot. This is just magnitude of h of j omega versus omega, and this red curve shows the frequency response, and it's compared to an ideal low-pass filter here in blue. So notice kind of what it shows is that at low frequencies, near 0 radians per second, the filter produces an output of 1. And we can see that here in the mathematical form too. If you set omega here equal to 0, you basically got 1 over 1, and which is 1. So this filter basically doesn't do anything to low frequency signals that are coming in over here. They go right through this filter without any change, okay? That's because this capacitor basically is invisible to low frequencies. It's almost like it's not there, so the output and the input voltages are just connected directly together. At higher frequencies, though, remember a capacitor acts more like a short circuit. And so this is a voltage divider circuit here, and the low impedance of this capacitor at high frequencies pulls this output voltage down towards 0. So as a result, at high frequencies, the filter basically blocks any signal coming in. It basically gets multiplied by something very close to 0. And again, this is not a perfect filter, but you can see it does the job. It acts as a low-pass filter. The other thing that I should mention here that's going to be important is that this, you can see it in here. If omega is equal to 1 over RC, then this becomes 1 plus 1, or 1 over root 2, which is 0.707. So this is called the corner frequency of the filter, or sometimes it's called the cutoff frequency. But we'll be using this term corner frequency here. And so for the RC filter, the corner frequency can be defined as 1 over RC. Okay, so let's look at how we can construct a Bode plot for this filter. So we've got the magnitude of frequency response right here. So remember, for a Bode plot, we need to take 20 times the log of the magnitude. So we're going to have 20 times the log of this function here. Now, one of the tricks when using these magnitudes here is they almost always have a square root in there, because we're using Pythagorean theorem to find the magnitude. So this square root, remember, is the power of 1/2. And since this power of 1/2 is in the denominator, it's a power of -1/2 if we think of it on top. So we can rewrite this function right here on the right side as 1 plus omega RC quantity squared, all to the power of -1/2. And the reason we do that is because now we can use the properties of logarithms. So if you're a little rusty on logarithms, now is the time to sort of review the properties. I've put them here so that you can look over them. You know, you learned all these long ago in high school. But for example, the ones we're going to use here are log of a to the b is equal to b times log of a. We'll use that over and over. Log of a times b is equal to log a plus log b. Log of a divided by b is log a minus log b. And finally, negative log of a is the same as log of 1 over a. So these are 4 real fundamental properties of logarithms that we're going to need to use. So right off the bat, we can use this first property here, and we can take this minus 1/2 and bring it out to the front. So the 20 turns into a negative 10, and now we simplified this a little bit. We got rid of that exponent. It's log of 1 plus omega RC squared. So this is the actual result that if you were going to plot this using, say, a computer like Excel or MATLAB or something like that, you would use this function here to plot the magnitude as a function of frequency. But we can do a little bit more by hand here. We can find some asymptotic approximations. In other words, how does this filter behave at extremes of frequency? For example, at really low frequencies. All right, well, that's pretty easy. The low frequency approximation is we just let omega here approach 0. So what happens to this term up here? We end up with 1 plus 0, which is of course 1, and we all remember that the logarithm of 1 is 0. So at low frequencies, are in decibels, this filter has an output of 0 decibels. Okay, so 20 log times, of the absolute value of h of j omega is equal to 0. So that's our low frequency approximation, 0 decibels. Now what about high frequencies? Well, if we let omega get very large, then this 1 here is not going to be a factor, because this term on the right is going to be much, much larger than 1. So, for all practical purposes, we can ignore the 1. So what happens when we ignore that 1? Well, this 2 up here now can be brought out in front. All right, so actually I've done it down here. Let's go through the steps. So here's the total frequency response. If we let this term be larger than 1, we can approximate it as negative 10 log of omega RC squared. Now this 2 up here, bring it out in front. We have negative 20 times the log of omega RC. And now we're going to use this log property here, the second one, and split this up into two, this product here, split it up into 2 logs. So what happens here is we have negative 20 times log of omega, that's the first term, minus minus 20 times the log of the other term, which is RC. So if for high frequencies, our Bode plot is going to look like this function here. Now, what does this mean? Well, remember what we're plotting here is on the y-axis, we're plotting 20 log of magnitude h of j omega. So this is like our y. And on the x-axis, we're plotting, because remember, we're doing a log plot, we're plotting log of omega, basically, if we think of this, like a log-log plot. So this negative 20 out in front gives us the slope of the plot, because this is the number in front of the x. Log of omega is like our x. So this would be, y equals mx plus b. And I'll show, and actually I've got it written here, I'll show this also on the next slide in a little more detail. This second term here, we're not going to worry about right now. Obviously, this would be the y-intercept if you think about plotting a line. But the key thing here is that the slope of this plot at high frequencies is going to be negative 20. Now, what are the units? Well, it's negative 20 decibels per decade of frequency. Let's take a look at this in a little more detail on the next slide. So this is, again, some more detail on interpreting the slope of the Bode plot. So, here was our result from the last slide. We have 20 log of magnitude h of j omega. We can think of that as our y. We got minus 20 times log of omega, but since we're plotting log omega, right, in units of decades of frequency, where each decade is an order of magnitude, then log omega is like x, so therefore the minus 20 is our slope, m, and then this is our y-intercept over here, 20 log of RC. So, again, the key thing here is that this slope here is negative 20 decibels per decade. Now, what does that mean? Well, what that means is that the slope of this curve here, it's a straight line, and every decade in frequency, it's going to drop by 20 decibels. So notice we go from 40 decibels here down to 20 decibels, and that happens over 1 decade of frequency. So this is, and it's a negative slope, right? It's going down. So the slope is negative 20 decibels for each decade of frequency. And then you can see, when we go from 20 decibels down to 0 decibels, that's another negative 20 decibels, and it occurred over 1 more decade in frequency. So this is, is a little just different way of showing how to plot frequency response versus frequency here. The other thing, which actually we don't have to worry about too much here, but this last term here, minus 20 log of RC, we can do a little trick here. This minus sign, we can turn it into a plus sign if we put a minus 1, raise RC to the minus 1 power, which becomes 1 over RC. And for this example over here, I put in some values where RC, which is, by the way, this is the RC time constant, right, of the circuit, is 1 millisecond. So 1 over RC is 1,000 radians per second. And this B term, this y-intercept, is 20 log of 1,000. And log of 1,000, of course, is 3, right, because there's 3 zeros. And so 20 times 3 is 60. So 60 decibels would be the y-intercept. And you can see for this curve here, if you were to continue moving up here, you would actually intercept over here at 60 decibels. So let's take a look at what happens when the high and low frequency approximations are set equal to each other. So what we've shown so far is that at low frequencies, in other words, this portion of the graph here, our Bode plot for this filter is at 0 decibels, right? So this dotted line right here is what we call our low frequency asymptote. And likewise, we showed that at high frequencies, the slope is negative 20 decibels per decade. So let's find what happens when we set these two asymptotes equal to each other. All right. So what I've done here is I'm going to set the low frequency asymptote, which is 0 on the left side, equal to the high frequency asymptote, which you'll remember is this function here, negative 20 log omega minus 20 log RC. Put that on the right, and we're going to set them equal to each other, basically, so we can solve for this intersection point right here. So this is actually, it looks, kind of messy at first, but it's actually quite easy to do. Let's take this term here and move it over to the left side. So it becomes 20 log omega equals minus 20 log of RC. The next thing I can do is divide both sides by 20. So I get log of omega equals negative log of RC. And let's get rid of this minus sign again, just like we did on the last slide. This minus sign can go up here as an exponent. In other words, RC to the negative 1 power, and that's just 1 over RC. So now I've got log of omega equals log of 1 over RC, so I know that these arguments of the log function must be equal to each other. Therefore, omega here is equal to 1 over RC, and remember, 1 over RC is the corner frequency of the filter. So these two asymptotes intersect at the corner frequency. And in fact, this makes sense. This is why we call it a corner frequency. You can see there's a corner here in the frequency response, right at omega sub C, or the corner frequency. And depending on the value of R and C, this corner frequency will move around. You can set it to whatever you want, depending on what values of the resistor and the capacitor are used. So now we've got these asymptotes set up like this. There's one other thing we can do here, and that is actually, before I talk about this down here, let me just point out one more thing here. Again, notice the asymptote here, the high frequency asymptote. So it starts here at the corner, and it drops 20 decibels for every decade in frequency. So if this is the corner frequency here, the next decade would be 10 times the corner frequency. And the next decade over would be 100 times the corner frequency. And you can see for each decade, we drop precisely 20 decibels. So we go from 0 to -20, and then -20 to -40 here. All right, the next thing we're going to do is let's find out what happens actually right here at this corner. So at the corner, we're going to determine how many decibels this curve, the actual curve, really is, because we know these asymptotes are valid near 0 and way out here at high frequencies, but at middle frequencies, those around the corner, these asymptotes are only approximations. So let's find out how close it really is. So if we plug in the corner frequency, which remember is 1 over RC, so this omega here in our frequency response becomes 1 over RC. So we have 1 over RC times RC. So this is 1 plus 1 squared, right? Which is 1 plus, here it is here, 1 plus 1 squared. So that's 2. And so we have 10 times the log, oops, I forgot a minus sign there. There should be a negative sign there. Here's the minus sign here. So we have minus 10 times the log of 2. And on your calculator, if you calculate the log of 2, it's 0.301 times negative 10 is -3 decibels. Okay, so what this tells us is that right here at the corner, the actual frequency response is not 0 like it shows up here on the asymptotes, but it's 3 decibels below that. It's -3 decibels, which on this graph, remember this is -20 down here. So -3 decibels is somewhere right around here. So this allows us now to sketch this red line, which is the actual frequency response of this filter. So we follow the asymptotes here at low frequency and here at high frequency, and then near the corner we know that we have to dip down by about 3 decibels. So I can kind of draw this curved line like this. And so this is a way to sort of hand plot a Bode plot without using a computer to actually graph this. And so this is an important skill to have, to be able to do some hand sketches like this. By the way, remember that the corner here corresponds to that corresponds to 1 over RC, but it also corresponds to a magnitude of frequency response equal to 0.707, which is 1 over square root of 2. So this, the gain here of this filter, it's 1 here. The filter, remember, it passes all frequencies, so it has a gain of 1, which is 0 decibels. And then at the corner frequency, the gain is about 70%, 0.707, which on a Bode plot corresponds to 3 decibels. All right, what happens if we add a second RC filter stage? So in other words, if we have this is called a first order filter. We talked about this back in chapter 3 here, and then we send that output through another first order filter. Well, then we have, in essence, constructed a second order filter. And remember that, this isn't, now we're going to see another advantage of using a Bode plot. In the frequency domain, the total frequency response of these two systems in series are just multiplied by each other. So we'd have H1, which is this guy over here, multiplied by H2, which is this one here. But in Bode plots, we're using the log of the frequency response. So remember that logarithms of multiplied factors are additive. So when we take 20 times the log of the total frequency response here, we get 20 times the log of H1 plus 20 times the log of H2. And so we can simply add the individual Bode plots to each other. So instead of this red one shown like this, which is the one we just did, the first order one, negative 20 decibels per decade, when we add another one of these to it, we get a second order filter, which is this blue line, and the slope doubles. It's now negative 40 decibels per decade. And by the way, this point right here would be at 6 decibels below the corner, not 3 decibels. So the key thing here is for the second order filter, the slope is twice as steep, so it's falling off at twice the rate in terms of decibels per decade, which is desirable because we want the filter, remember, ideally it just falls off like a brick wall. So, we can kind of take this to the limit when we get to higher and higher order filters. Again, the first order filter has a slope of minus 20 decibels per decade. Second order filter would be minus 40. Third order filter minus 60 decibels per decade. And a fourth order filter would have a slope of minus 80 decibels per decade. And you can see this purple line here is starting to look more and more like the ideal brick wall low pass filter, which is shown here. The next thing we're going to look at here is sort of an efficient and clever shortcut method for, again, for doing hand-constructed Bode plots. And this will be useful for parts of the homework that you're going to do for this chapter. So the idea here is, what we just learned is for the ideal or for the RC low pass filter that we just looked at, we saw this result. The frequency response was 1 over 1 plus j omega RC. And now this is not magnitude, right? This is just the frequency response in its full complex form here. And we also learned that the corner frequency, omega sub c, was equal to 1 over RC. So if we replace RC with basically 1 over the corner frequency, we get this form here. So it's 1 over 1 plus j omega over omega c. And we saw that for this filter, we have a Bode plot that looks like this. It has, it's at 0 decibels until we get to the corner at the corner frequency, and at that point we start dropping by 20 decibels per decade. Okay, so if we have by extension now, if we have any system that has the following frequency response, 1 over 1 plus j omega over a, all right, well this a here, notice, is where the corner frequency would be up here. So we know that a is equal to the corner frequency. So we could plot this system here using these results here. We have 0 decibels up to the corner frequency, which is a, and after that this thing starts falling at 20 decibels per decade. So this is the frequency a, this would be 10a, this would be 100a, 1000a, etc., etc. Now, there's another form of this. Instead of 1 over 1 plus j omega a, if we have a frequency response that looks like 1 plus j omega a without the fraction, then once again, by doing the full analysis, which I'm not showing here, this a is again equal to the corner frequency. And the only difference is now, instead of this thing falling down at 20 decibels per decade at the corner, once you get to the corner, it moves up at 20 decibels per decade. And this is not a complete surprise because remember, this is a reciprocal here and there's no reciprocal here. And so when you take a log of this, the only difference is a power of -1. And that power of -1 leads to a minus sign in the slope. So instead of the slope being -20, the slope is +20. There's a couple other useful forms that we can use when we're going to do this shortcut method. So if we have a frequency response, h of j omega, that just has the form j omega over a, all right, not 1 plus j omega over a, but just j omega over a, then what happens here is by doing, I kind of showed the steps here, but I'm going to skip that. The key thing is what we end up with is just a straight line in the Bode plot, and it passes through 0 decibels at that frequency A, and it has a slope of positive 20 decibels per decade. All right. Likewise, if we have a frequency response h of j omega that's 1 over j omega over A, then it's easy to show that the Bode plot for that looks just like this one, except the slope is a negative 20 decibels per decade. And again, it passes through the axis here, the frequency axis, at at 0 decibels. It passes through at that frequency A. So here is a summary of the 4 terms that we're going to need to use this so-called shortcut method. If we see anything that looks like 1 plus j omega over A, it's going to look like this plot here. All right, it's going to have a corner at A, and it's going to go up by 20 decibels per decade. If we have a term or a frequency response that's 1 over 1 plus j omega over A, then it's going to be at 0 until we get to the corner at A, and it's going to go down by negative 20. And then the other 2 are the ones we just showed. If h of j omega is equal to j omega over A, we have a straight line. Notice there's no corner here. It's just a straight line that goes through the frequency of A at 0 decibels, and it has a positive slope of plus 20, and this term 1 over j omega over A goes down by 20 decibels per decade, and again passes through the axis at A. So these 4 forms here, and their 4 graphs, we can use these to construct a Bode plot in theory for any frequency response that we're given. And this is the so-called shortcut method, which I'm going to show you next with some examples. So here is this shortcut method for Bode plots. So suppose that we're given a frequency response and it's in the following form. So notice the numerator and the denominator have been factored. So with this factored form, what we want to do is make all of these terms here look like one of those forms on the previous slide. So here's the trick. If we've got something that looks like A plus j omega, we can factor out that A, whatever this number is, in front. So we have a 1 plus j omega over A, right? Because notice if you distribute that A back in, you get exactly this. So what we can do here, with this first term, we have A1 plus j omega. Let's pull out the number A1 out in front, which leaves us with 1 plus j omega over A1. The second term, A2 plus j omega, let's pull out the A2, and we have 1 plus j omega over A2. And we can continue this for as many terms as there are up here. And likewise, down in the denominator, we can do the same thing. This term here, B1 plus j omega, pull out the B1, bring it out here, and we have 1 plus j omega over B1. Next term, B2 plus j omega, pull out the B2, there it is, and we have 1 plus j omega over B2. And again, repeat this as needed until all these terms look like this form here. So this is now, we can rewrite this thing as a cascade connection of subsystems in series. In other words, all these terms here are multiplied together. So out in front, we have all these constants. Whatever this first A was here, multiplied by all the A1, A2, A3, divided by the B1, B2, B3. These are just a bunch of numbers. So let's put those all in front. All these terms on top here, we can think of those as multiplied together just like this, all right, in series. So this is the first term, second term, and we just keep going. Now the terms on the bottom, remember these are in the denominator. So if we're going to multiply them, we need to write 1 over 1 plus j omega divided by B1, and then this term here would be 1 over 1 plus j omega B2. So we're just taking this form here and we're just expanding it out. We're thinking of expanding it out term by term where each term is multiplied together. So now each of these terms here can be represented by a subsystem which is in series with the one next to it. So what we can do is use those shortcut, basically the summary from the last slide, all those results. We can write the Bode plot for each of these and simply add them together. So let's see how this would work. And I'll go through a couple more examples in the next slides that have a few more numbers in it. But here's the main idea. This number out in front is just a number. And so we have to convert it to decibels. Well, that's easy. We just multiply this number. Take the log of this number and multiply it by 20. So that's going to be H naught. All right, that's this line here. So in my example, let's say it turned out to be 10 decibels. So I would plot that right here. Okay, and notice it's labeled H naught. The next one is this term here, which we'll call H1. Well, H1, if we look at it, this form here, remember from the previous slide, we have a corner at A1, so whatever frequency that is, and it starts at 0 decibels until we get to A1, and then it goes up by 20 decibels per decade. So that's H1. H2, same thing. We're going to assume that A2 is different than A1. So A2, let's say, is greater. So it's over here. So we have 0 decibels until we get to A2, and we go up by 20 decibels. All right, and we repeat this. If there are more terms, we repeat it. Now let's deal with these. Well, these guys, remember from the previous slide, they are somewhat similar than these, but the slope is negative. So this one has a corner at B1. So again, we start at 0 decibels, we go all the way until we get to B1, and then we drop at negative 20 decibels per decade. That's the slope, and that's what I'm calling H3. And then here's H4, has a corner at B2, so you can see out here is B2. So we go start at 0, it's a straight line at 0 until we get to B2, and it goes down by 20 decibels per decade. So now we've got all these asymptotes written here. And remember, for a Bode plot, this is one of the powers of using the Bode plot. Because it's logarithmic, these products, when we take logs, we just add the logs together. So all we have to do is add up all these asymptotes. So notice at low frequencies here, we got all these are 0, so they don't contribute anything. It's all H naught here, which is something like 10 decibels. So that's this line here until we get to A1. Now what happens at A1? Well, now this blue line starts moving up at 20 decibels per decade. So my black line is going to go up at 20 decibels per decade. Once I get to A2, notice this green line for H2 kicks in. So I've got 20 decibels from the blue line plus 20 decibels from the green line. So my new slope here is 40 decibels. So the slope increases. Once I get to B1, I've got plus 20, minus 20, because of H3 has now kicked in. So 20 plus 20 minus 20 is plus 20. So the slope is still positive, but it's only 20 now. Once I finally get to B2, I'm adding all my asymptotes now. So I've got plus 20, minus 20, minus 20, which of course is 0, right? We've got 40 minus 40. So the slope of this thing zeroes out and it's flat again, it's horizontal. The final step then is just to sketch, in red, the smooth line that sort of connects these asymptotes. Remember, at the corners, it's never exactly equal to the asymptotes. It's typically 3 decibels below or above the corner accordingly. So this red line here is our final estimate of what the Bode plot for this, very complicated frequency response looks like. Let's go through another example now. This one's a little more specific because it's actually got some numbers in it. This one is example 6.5 in your textbook. And also, I should mention again that in the worksheet or homework for this chapter, you'll be doing some problems very similar to this. And the idea here is that you can construct a Bode plot very quickly by using this shortcut method. It's actually very efficient and simple once you know how to do the method. So let's go through this one and see how this works out. So you're given the following frequency response. H of j omega is equal to 100 times quantity 1 plus j omega over 10 plus j omega times quantity 100 plus j omega. So remember, the goal here is, let's first take this 100 and put it out in front here. And this term here, 1 plus j omega, that's already in the proper form, so we can leave that as it is. These terms down here, though, I got to get rid of this 10 here. So I'm going to factor out this 10 and put it out in front here, and what I'm left with is 1 plus j omega over 10. Likewise, the second term, I got to get rid of this 100, so I bring that out down here, and this term becomes, 1 over 1 plus j omega over 100. So we've just rewritten this function up here. I've just rewritten it in a different form here that we know how to handle. The next thing I did was I'm going to call this first term out here H1, the second one H2, this term H3, and this term H4. You can think of these as 4 different subsystems that are all connected together. So the first thing we're going to do is find out how many decibels is H1. So I take H1, which by the way is 100 divided by 1000, which is 0.1. I take the log of it, and you can actually do that in your head. That logarithm is -1, and multiply that by 20, which gives me -20 decibels, and it's constant, right? This is just a number. So the first thing I'm going to plot is H1, which here's my Bode plot for asymptotes. This light blue line here, which I labeled H1, is, notice it's plotted at -20 decibels. All right, so there's that. And then we have to find the slopes and the corner frequencies by inspection for H2, H3, and H4. All right, well, this is all pretty straightforward because now we know the shortcut. So 1 plus j omega, you can think of this divided by 1. Okay, you don't see that, but it's there. It tells us that there's a corner frequency at 1. And since this is not in a fraction, we have a slope of plus 20 decibels per decade. So H2 is shown here in green. So we start at 0, we go straight across till we get to the corner frequency, which we just determined was 1 radian per second, and then we go up by 20 decibels per decade. All right, H3 is this term here. First of all, I can see immediately the corner frequency is at 10. And also, since this is one of those forms where it's 1 over 1 plus j omega over 10, I know that the slope is going to be -20 decibels per decade. So I start at 0, I go straight across till I get to, right here, at 10. There's a corner. And then this red line goes down at -20 decibels per decade. That's the slope, and that's H3. All right. And again, remember what this slope means. If I start here at 0, I'm going to drop down to -20 decibels in 1 decade. So I'm going from 10 to 100 in frequency. That's a decade. My slope has to be exactly -20 decibels. All right. And likewise, from here to here, I go from -20 to -40, and that's 1 decade going from 100 to 1000 in frequency. The last one we have to do is this last term, H4. You can see by inspection, corner frequency is 100. And again, this term is just like this one. It has a slope of -20. So this time I start again at 0. I go all the way out here till I get to the corner, which is at 100. And then I drop down at -20 decibels per decade. That's H4 labeled right here. So now I have all my asymptotes plotted on the same graph. And the next step is I just have to add all these asymptotes together to get our final, which is shown here in black. So how do I do this? Well, notice at between 0.1 and 1 radians per second, all of these are 0. And all I have is a -20 decibels. So that's going to be my graph here. It's going to be at -20 decibels. All right. Once I get to this corner, I know that it has to start going up at a slope of 20 decibels per decade. So once I get to this corner at 1 radian per second, I go up at 20 decibels until I get to the next corner, which is right here. And now this -20 cancels this +20 up here. So the result is 0 slope. So once I get here, I just go straight across with 0 slope. And then when I get to 100 radians per second, I'm at this point right here. Now this purple slope kicks in, which is another -20. So I've got a +20 going up, a negative 20 going down and a negative 20 going down. So the net is negative 20 again. So my final slope over here, everything to the right, is going to be negative 20 decibels per decade. And I can finally fill in with the red line here is just to smooth out the corners, as we know happens, and follow the the asymptotes and just smooth and round the corners. And there is our Bode plot for this frequency response shown up here. Here's another example that's just a little bit different. This is actually a bandpass filter. Here is the frequency response. H of j omega equals 1000 j omega divided by 10 plus j omega times 1000 plus j omega. So as before, we're going to first take care of all these numbers in here and bring them out front. So here's a 1000. Let's bring that out in front right off the bat. And what's left is just the j omega by itself. Here we have a 10. So let's bring that out down here in front, leaving 1 plus j omega over 10. And then this 1000, we're going to factor that out and put it out here, 1000, leaving 1 plus j omega over 1000. So now we can write these actually, let's see. The way I did this is I combined these two into one. So notice what we have here. We have 1000 divided by 1000. Those cancel. So really we have 1 over 10. So I'm going to write this j omega over 10 and just put that out here because this is one of those forms that we know how to handle from a couple slides back. So let's call that h1. And then this term here we'll call h2, and this term here we'll call h3. So we have 3 terms to plot. So for h1, if you look back a couple slides, whenever we see something that has a form of j omega divided by some number, we have a straight line. That's this, there's no corner, it's just a straight line. And remember, the straight line goes through 0 decibels at this number, which is on the bottom here. So at 10 radians per second, we know this thing goes through that point on the horizontal axis there, and it has a slope of plus 20. So for H2, this term, we see that we also have a corner at 10, which is again right here, but this term here, remember, starts at 0 until we get to the corner and drops at negative 20. And the same with this term here, we have a corner out at 1000 over here, but we start at 0, we go to the corner, and then it drops at 20 decibels per decade. So we've got all our asymptotes here. Now the last step is we just need to add them together. So for low frequencies here, again, these zeros do nothing. All we have to take account for is this green line here, which has a slope of positive 20. So that's shown right here, this portion here. Once we get to this corner right here, notice we've got one slope going up at 20 and one slope going down at 20. These two cancel each other, and the red line, of course, has no slope anyway. So the net slope between here and here is 0. So you can see this thing flattens out and it goes straight across. Once I get to 1000, this corner here, this red line kicks in and contributes negative 20 decibels per decade. And remember, the green and the blue are canceling each other. So the net effect is minus 20 decibels per decade, which is shown right here. And we're done. And then finally, the last step is just to fill in the red line, which is the smooth curve approximation to these asymptotes. And so this shows what a bandpass filter looks like on a Bode plot. So remember, a bandpass filter, what it's doing is it's passing frequencies between 10 and 1000 radians per second. That's the pass band. And then everything less than 10, it's going to fall off. Remember, this is a log scale. So this is falling off, relatively quickly, 20 decibels per decade. And then likewise for higher frequencies out here above 1000, where also the gain or the frequency response of the filter is falling off logarithmically also. And so basically what this is doing is just passing these frequencies here inside the passband. So basically, that's pretty much it for the content of this part of the lecture, I just wanted to point out a couple of subtleties here. One of the issues that comes up, and we haven't really looked at the phase plots here, but there is an issue that I just wanted you to be aware of when you're plotting the phase of a Bode plot. So remember, and I don't need to go through all this, this is just a review of complex numbers, but this phase angle, if we represent a complex number as a vector in the complex plane, then this angle here, theta, represents the phase of this complex number z, and the length of this vector, r, represents the magnitude of the complex number. So right now what we're concerned with is this phase here, theta. And remember that we can think of theta is the inverse tangent of b, the height here, divided by a. But we have to be a little bit careful when we use this definition of theta because it depends on which quadrant of the graph theta falls in. So let's take a look at this just real briefly. So, this is shown, there are 4 graphs shown here, and, in all graphs, this is the same complex plane, but we're showing z here is in the first quadrant, here z is over here in the second quadrant, z is in the third quadrant, and z is in the fourth quadrant. So it turns out that when we use, this definition of phase angle theta as inverse tangent of b over a, what we have to be careful about is that minus signs, if both of b and a are negative, we'll end up over here in this quadrant, and those minus signs cancel each other in this calculation here. But we have to subtract pi from the answer that we get in order for the angle to be over here in this quadrant. Likewise, when we're over in this quadrant, we have to actually add pi to the phase angle. So I won't go through this in detail right now, but here's a summary of the results. The phase angle of a complex quantity, it depends on the sign of a and b, where again, a is the real part, b is the imaginary part. If they're both positive, we can just use the phase angle is just equal to inverse tangent of b over a. Likewise, if a is positive and b is negative, we can also use this same expression. However, if a is negative and b is positive, we're going to end up in this quadrant. And if we just use, inverse tangent of b over a, we'll get an incorrect result. So the way to remedy it is we have to add pi to the result. Likewise, if we're in this quadrant down here where a and b are both negative, we have to make sure we subtract pi from the result of using the inverse tangent function. And the last 2 slides here are basically saying the same thing. When we're taking a frequency response, h of j omega, and we're finding the magnitude and phase, we're basically we're breaking up the frequency response in rectangular form into a real part and an imaginary part. And so I call the real part a of omega and the imaginary part b of omega. And in order to find the phase, we're going to use the inverse tangent of whatever b is divided by whatever a is. But again, we have to be careful with the signs of b and a. And so our last slide here, again, this is just a summary of the sign of a and b. When we take the phase angle using the inverse tangent, there are some times when we can just use inverse tangent by itself, and these basically in this quadrant and this quadrant. But if you're in either of these quadrants, the second or third quadrant, you have to either add pi or subtract pi to your result to get the correct phase angle. All right, so that is it for part 1 of chapter 6. I will see you guys shortly in part 2, where we'll talk about LRC filter design. Take care and goodbye.